program management or with, I got as far as project leader, but program management, I started speaking my mind a little too freely. Suddenly I'd be doing other things.
When I got to assessing, that's how I ended up. What I didn't know is when the guy hired me, I was his replacement. He didn't tell me. I just want to do circular, but yeah, so I ended up with a group.
Is this like, is it
So I was getting up and I gave a presentation on stuff and I was saying, why didn't you do this? And I said, because it costs like, it costs $100 an hour to run this, and I programmed it. It's the truth!
Well, you spend $800 an hour trying to work your way around all these other fixes this way.
The thing is, we were presenting against folks from Johns Hopkins who had a cheaper tunnel, and they were saying you can get just as good. Well, no, not actually, smaller, but yeah, they were shaping the walls to preserve area. So that's great if you know what it's supposed to look like, but if you knew what it's supposed to look like, then why are you doing the test?
Yeah.
Validation verification.
Yeah, thanks.
Yeah.
Okay, yeah, well, I'm gonna go try to hunt down, Jeff next.
Okay, great.
At the very least.
Can you get my email about the
project
evaluations?
And there are some students that are like super lopsided.
Yeah, I've got I didn't get your email, just when you send it.
This morning.
Okay, you probably haven't gotten into my, but yeah, I've got a number of,
a little bit longer than
students, okay, so,
just a so it's not a big deal on that. So
we're just gonna work on the one.
we get the hubs and sections hubs and
So like, do we reach out to them or do we?
I'm going to be, I'm going to be reaching out and, in fact, already talked to the person to throw staff problems to, and there's 3 or 4 at this point. Okay, thank you for noticing.
Yeah, I was noticing there's some people that just were very low, and I was wondering what we're supposed to do about that.
Yeah, well, first thing I need to get the grades so that we I'm just going to contact people who are
So, so I didn't grade the homework yet, but I have graded some of them, and basically I saw like a 2 solution which is quite good. So I just upload. One sec. Another one is this too. Right. So yeah, in the meantime, before I grade everyone solution, maybe you can compare your solution with the one by Yitang and Yahweh. But I will try to grade it soon. Yeah. And now, for today, we're gonna basically finish the discussion on the cut matching game. And all right. It doesn't look that good. One sec. Sorry. Okay. Okay, let me recall about the card matching game a bit, right? So the card matching game is the framework for building an expander where there are two players, the card player and the matching player. And the card player wants to build the matching as fast as possible, and the matching player try to slow this process down. And the game, the process proceed like this. That is, in each round, the card player choose a card, and then the matching player just need to choose some matching, add a matching that cross this card. Yeah. And basically, the size of the matching must be of size A. So meaning that the guy on the smaller side, everyone is matched. Yeah. Okay. And we have seen and basically for each round we get GI, which is basically you add a matching into your graph again and again, and you want that after some round you get an expander. So we have seen one algorithm, which is the deterministic algorithm. And the deterministic algorithm is very straightforward. So we have seen that the very straightforward heuristic for the card player is that for each round you just need to choose a card which is balanced, and also it should contain a sparse card in it, or itself should be maybe either itself is a sparse card or it contains some sparse card. Yeah. And basically in the deterministic algorithm here, we really just do that. We keep finding balanced sparse card until that cannot happen, you cannot find it. And then we prove that if that once you cannot find any balanced sparse card, then it must be the case that at that point the graph is such that there are some small part AI, and such that the complement of AI here, BI here is already an expander, right? It's big already. And we show that once you have this, then whenever you just add a matching from A to B, then you get an expander at the end. So that's the deterministic algorithm, and we have analyzed it, and it works. And now the bad thing about deterministic algorithm is that it can be quite slow. Asking you to find a balanced sparse card can be slow, or at least it's not super clear how to do fast. Now we also look, so this is why we look at like randomized algorithm here. So for the randomized algorithm, like in each round, the cut player would need only like linear time or nonlinear time, and there will be just log square rounds. Yeah. So okay, I will just try to recap things. So first, we have okay to describe the algorithm itself. Let me recall the matrix PI. Yeah. PI is just a matrix that in each entry of PI is like entry UV of PI is this thing. Can someone recall what have I defined? How did I define PI UV? So this is just the probability of a random walk that like this is like some particular random walk that start at U and end at V after I step. Okay. And do you recall what is this random walk? Like, how did we define this process? Right, right. So it's a random walk such that, like, if you are at node V in route I, and if there is a matching that match V to V prime in route I, then you go to V prime with probability half, and otherwise stay at V with probability half. And if you are not matched, then you just stay in this round. And in the next round, you look at the matching in MI plus 1 and so on, right? So that is a random walk process. And because we define the random walk process in this way, then we have that the ith column of this matrix is basically like the ith column of this matrix, which is basically the total, like you kind of look at the mass that end at the vertex A at route I, right? You have two cases. If A is not matched in this route I, then the mass that end at A is the same from previous round. Otherwise, if it is matched at route I, like if A is matched to B, then what you do, you really just like from both perspective of A and B, like you stay at A with probability half, or you move to B, and the same thing happened to B from B perspective. So this is why the vector is updated like this. Okay. Yeah. And if you define, like, by this definition, I can write Pi from Pi minus 1 by multiplying by matrix M, where the matrix M is just like this. All right. Okay. So I'm just keep I need to recall things, but yeah. And so from this definition, you can see that Pi is nothing but like P0 times M1, M2 up to Mi. And P0 is I, right? Okay. Okay. And the ith column of Pi is then this thing times the indicator at vertex A. Okay. All right, now we can describe again the randomized algorithm. Any question up to this point? Okay. Yeah, the randomized algorithm is the following. Is that like in round I, what you do, you choose a random unit vector, Ri, such that it is orthogonal to all one vector. And then you compute this thing. You multiply Ri to this whole thing. How fast does it take, by the way, to compute this thing? So how fast does it take to multiply Ri to M1? So it's gonna be just ON. And the reason is that you can see that this matrix Mi will actually have only ON non-zero, right? Like you either have like if for each of the node, if it is not matched in this round, you have one non-zero. If it is matched, then you have if it A and B is matched, then you just add like this half four non-zero into the matrix. So like each of the node generate either one non-zero or two non-zero into the matrix. So Mi is sparse. It's just ON, non-zero. And when you have any matrix M and you multiply it by V on either side, that takes just non-zero of M time, right? Because you don't ever need to look at the zero entry. You just look at the non-zero entry and multiply, right? So because of this actually takes just n time. And then once you multiply this thing, you can multiply the resulting here to this thing. And that takes another n time. So in total, this takes like ni time, right? So it's not good to multiply like a matrix, the whole thing here first. It's good to multiply one vector to a matrix and look at the resulting vector and multiply again. Yeah. Okay. So, okay. So you can see that X can be computed very fast. Yeah. But X also have a meaning, right? Because you see that Pi is this thing. So it means that X is just simply I times Pi minus 1. Yeah, but again, it's not good to compute Pi minus 1 explicitly because that's slow. Yeah. but here we have the interpretation of x. And once you have compute x, then you compute you sort the vertices by x value, and return the median cut. That is like look at like let AI to be all like n/2 vertices with like with smallest value in x, and let that be AI. Right. Okay. The algorithm is clear, right? Okay. And now, okay. Let's interpret x a bit more. So again, you have that. What is xa? Like, so because x is just simply this vector ri times pi minus 1. So xa is just ri times the 8th column of pi minus 1, right? But that is just like, you just think of each node A, you associate A with this vector, which live in R to the n. And then like each node A is like in some space, basically. And then you just really just project everything down to some random direction, Ri. And then so you look at this will be xa. Yeah. Okay. Okay. Yeah. So like you have nodes, like each node. If you think of each node as this point in space, like they are like kind of scattered around, and you just choose one direction and project everything into this line. Yeah. Yeah. Okay. So that's xa. Yeah. And last time I tried to tell you like an intuition why this algorithm is good. Okay. And the intuition come from like, at least my intuition, like come from the fact that this is like similar process to power method. So the set AI should contain a balanced sparse cut if that exists. Yeah. Okay, but I will skip this intuition today, and I will proceed now to just the analysis, why this thing works formally. Okay, and similar to deterministic algorithm, recall that the goal the goal that if we can prove it then is enough is that if we can show that after some round, then we have that pi u to v, like the probability that the mass from u to v after I step is kind of uniform for every pair. If that happens, then we are good, right? So that is still our goal. Yeah. And we actually will prove that this will happen actually when I is log square, and this will happen with high probability. And to really prove this, we will use some potential function to measure the progress that we go towards this goal. Yeah. And the potential function will be kind of different from entropy potential. This time it's going to be L2 potential. And the potential is like this. So we say that a potential at vertex A is just this column of like the potential at vertex A at the ith round is just the eighth column of pi. The difference between eighth column of pi and the all one, like this uniform distribution here. So you think of this thing as like the distribution of mass that ends at A after time I, right? Like there are many mass from many nodes. So you look at so this is A, and there are like total mass at A at any time is 1, right? And you kind of look at this as like the distribution, like this is from U1, this is from U2, and so on. So this is like this is the Pi at A. And you look at this and you look at the difference between here, this thing and the uniform distribution, and basically take the norm and square. Yeah. So basically this thing measure how much the mass at A after I step, how much it is concentrated. So if it is very far from uniform, then this thing gonna be big, right? If it is completely uniform, then it's gonna be 0. Yeah. So the bigger it is, the worse it is. Yeah. Okay. And so actually we can really compute it. At time 0, this thing is basically 1. Because like at time 0, the mass at A is just like this thing is just the vector 1A, right? So and you can just compute it, and it should be basically 1. Right? And yeah, and this is gonna be 0 if and only if you get uniform distribution. So this is kind of the opposite of the entropy function, where we talk about when we use it for deterministic algorithm last time. Last time we said that like from the beginning the potential start from 0. And it never be more than n log n. But this time, like last time, like when the potential is big, then it's good. This time, when the potential is small, then it's good. All right. Okay. Yeah. But it's just the reverse direction. We still really kind of try to measure how close it is to uniform distribution. And the total potential is just summing over all potential on every node. Okay. And basically, in the beginning, you have that the initial potential is basically n, and it's never less than 0. And we want to say that we kind of go. This potential approach 0 fast. Okay. So let's just verify one thing, that actually if the potential become very small, then this is indeed what we want. That is, if the potential become like 1 over poly n is very small now, then the graph must be an expander. And the reason is this. So if potential is very small, then actually for every U and V and I, then the mass from U must be sent to V with like, actually we can even say this, then Vi minus this is less than this thing, right? This is just by definition. If this is true, then you have this, right? Because this thing is really just summing, you just really sum over all U and V. Yeah. Okay. But if this is true, then it means that Pi of UV cannot be super small. It must be at least like 1 over 2n, right? And so basically every node can send some mass to every node now. So actually you will have that is like and it cannot be more than like is at least 2n, and also at least at most something like what? So really like the distribution is close to uniform really. And we have seen before that this is what we want. Yeah. But to make it formal, then we have that, okay, if you can send every like the mass from every U to V, then it means that with this much, then it means that if you look at the one product graph, then you can embed this one into GI, right? We have seen this. And once you can embed this, then it means that the expansion of GI is at least half. Yeah. So this is just like something that that we have seen. Okay. Question about this? All right. So now we know that if the potential is really small, then we are done. We just want to show that potential is indeed small. And to really like analyze this, we need to understand what does it mean like in each round, how much the potential will decrease, right? And it turns out that the reduction in potential is really like something that I will call like total square distance between the mesh node. So let's be more precise. Like this is just the potential decrease in each round, in round I. Then we will prove that this decrease is exactly this thing, 1/2 time for every edge that you add in the meshing. Like for each edge that you add in the meshing, here, you look at the two vectors and take the difference between them. Like this is the distance square of these two vectors basically, right? Like think of like U think of u. U is like, u is in, maybe think of this as some point of u. This is the point of v. So this is point of u, this is point of v. And this thing is nothing. This is nothing but the distance from point of u to point of v square. Okay. So this is the potential that, like how much potential decrease. And so note that if we can prove this, we can see that the potential never decrease, never increase, right? Because this is at least 0. So like you really never increase potential. Like you always go into the right direction. And if you know that the distribution at u for every mesh edge uv, the potential will decrease a lot. Like it's going in the good direction. The potential decrease a lot if the distribution that ends at u is very different from the distribution that ends at v. So this is how you should interpret it. Okay. So question about this? All right. So now we can prove it, and the proof is just here. Note that if A is not matched, then the potential at A doesn't change, right? So really, like the potential will change only for each matched edge. So now you look at each matched edge, AB, and just write down how the potential change. So this is the potential of A and of B before match, before like we do the we add a matching and we do the random walk step. This is the potential. And what is the potential after we do the random walk step? So both vector of A and B become this thing, right? You just really average them together. And you have the two terms here from A and from B. So this is just the potential of A and B after the random walk step. Okay. And now this is just to write down the definition. But and you can rearrange things a bit, and you get this thing like that. Like you just put this to be here and put this here. So this term you just put it, you just rearrange thing here. Yeah. Okay. But once we have it in this form, let's try to try to analyze it. So suppose that I write this thing as u and this thing as v, then this is also u, right? And this is v. So this is now u plus v minus 2 yeah. Okay. So this doesn't look that bad, but what is this? So we can look at this inequality. This equality, that is 2 of u square plus a of v square is this thing. And to prove this is like it's just algebraic. Like I see algebraic proof. I don't see geometric proof actually, but the algebraic proof is really here. That is, you can just look like what is norm square, right? Norm square is really just ui square, right? So now let me look at each index I, each index I. We have that for each index I. This thing is this thing, right? Sorry? This should be minus, right? Oh, plus, yeah, thanks. Okay, good. Oh, 1 sec. So this should be plus too. Yeah. Right. So we have this. Yeah. Because in each index, like they are equal in every index. So when you sum over all I, you get this. So this is a very algebraic proof, but I don't actually know how to look at this geometrically. Okay, but now we have that. Okay, so if I rewrite it a bit, right, then I can just write it like I divide it by 2 throughout the thing. And then I get this thing. So here I put 2 here because this is just 2 over 4. So I can, like, you see, right? Yeah. So now basically we have this. This is now exactly this thing. 1/2 square. So we can write it as this. By if you substitute u and v together, like how we define it, we get this. All right. So because of this, now like you can just, this is just a proof, but again, the interpretation here is that like look at each match edge, and how much the potential decrease is just how much the two distributions are different. How different the two distributions are at the two endpoint of the match edge. Okay. And now the intuition of the remaining analysis is this. So like we know that exactly that like, okay, think of each node as a point in n dimension, as I tried to tell you before. Like the point at A is just this point in the n-dimensional space. And suppose somehow, if the point of vertices, if this point of vertices are kind of well separated in this n-dimensional space, okay, like they are kind of well separated like this, and there are like a gap between two sides in this n-dimensional space, then you actually know that, like just from the proof before that, the great cut, the cut that is good for the cut player is this black cut. And the reason is that like for any two vertices on two sides here, right? No matter what matching, like, no matter what how you match any two vertices here, they're gonna be like they're gonna have large distance. And when they have like, so take A and B on different sides, they have large distance. And that will reduce the potential. Like the larger the distance is, the more you decrease the potential. And so like if there are like a bunch of them here and a bunch of them here, you must add a lot of matching here. And you decrease the potential a lot. But this is like something in n-dimensional space, and we don't actually really compute it, right? Like if we were compute it explicitly, and we can, like if we don't care about fast algorithm, we can really just compute this. But okay, we want a fast algorithm, and somehow we still try to find this kind of cut basically. But how do we do that without computing things explicitly? Like we don't work with this n-dimensional space. What we do is here. We just project every vertex to a random direction. And this is exactly what we do, right? We choose Ri. We project all the points of A into random direction Ri and call it Xa. And now the very nice property of random projection is that random projection kind of preserve pairwise distance with good probability. So if you choose a random direction to project, and if the two vertices were far in large dimension space, when you project it down, like there will be a lot of direction that they are still far after projection. And if they are close, then they are still close. So in expectation, the distance will be preserved. And this will like, you actually have some concentration as well. So suppose for now, like for your intuition, just think like you choose a good direction, and the pairwise distance between any two vertices are just preserved, right? And so what you get is something like this. You project everything down to just one line, but the things that were far away are still far away. But once you have this thing, then it's kind of easy to find a cut, because this is just one dimension thing. Just sweep through it and find a median cut. And that's the cut that we choose. And because now if we choose this cut, then the matching player needs, if for any matching that matching player add, he need to add a matching between these two things, right? Okay, some of the matching might have like small distance, but not many of them. So, and this thing gonna correspond to this kind of matching, so which is good for us. Okay, you see the intuition behind all of this, like. Okay, so now let me be precise. Yeah. So what I mean by like random projection preserved distance is this. So if you take any vector R V in dimension D, D-dimensional space, and if you choose a random unit vector R in this space, then okay. Then the distance, like the length in this, so okay. So maybe okay, yeah. V is here, and then you, let's say you project. This is R. When this used to be a length of V. And now if you project it to R, this is R times V. So we have that in expectation, the distance square here is just the distance square in original space over D. And this is like exact, like you have this. So basically the distance square, like the norm square kind of just reduced by dimension. So I will not prove this, but like intuitively, it should be kind of, like the intuition is just like, if you should, like there are basically most of the direction is good basically. Yeah. Okay, so this is the expectation. And we also have that, you can ask like, how much the distance square, like the norm square, after projection is much higher than what you expect. Like if it is higher than what you expect by a factor alpha, what is the probability that happen? And this event will decay decay exponentially on alpha. So I will not prove this, but yeah, this is gonna be something that, like, it is related to Johnson Lindenstraut. So you can look it up. This is something which is very useful, actually, like used for data science and so on. But I will just assume this thing. Okay. And now note that all the vector that we will work with actually will be in the n-1 dimensional space that is orthogonal to R1 vector. So when we apply this lemma to our setting, D will be n-1. So what do I mean by this all vector are in this space orthogonal to R1? Well, first of all, Ri, each random vector Ri, we are chosen to be like the guide which is orthogonal to R1, and among that, in that space, choose a random vector. Right? So that's by definition is in this space. Also, this thing is orthogonal to R1 vector as well. And well, the reason is just quite simple. Like both of them, both of them is a distribution. So some like you have two distribution and you minus two distribution to each other. The sum, like, okay. So should I prove this? Like PIUA for overall U is 1. So these are distribution and okay. this is just 1 minus 1. Yeah. So this is why this vector, the sum of all entry is of 0, which means that they are orthogonal to all one vector. And the same thing is here. Yeah. So really, like all the thing that we are working with is just in this space of n-dimensional space orthogonal to all one vector. Right. And now we have that this thing. Let's look at like let's say that like we match A and B together, right? And we have that the reduction in potential is this much. So this is gonna be exactly this thing. Why is that? Well, you can take a vector v to be this vector, and then you can see that r times v. So okay, like when you project v into random direction r, this is just a xa minus xb. Okay. All right. So now you have that this is v, and this is just this thing. So applying this lemma, you get this. Okay. And by if we can also say that like the distance between with high probability, these two things will not deviate by more than log n factor. So the distance after projection cannot be more than this distance square. Like the norm square after projection cannot be more than the norm square before projection by log n factor. Right? So are you with me? Or I just set alpha here to be log n, yeah, and apply it to here. So this side cannot be like the probability that this side is more than log n factor. Like the probability that this thing is like more, this is very small. This probability is less than 1 over poly n. So that's why you have this thing. Okay. All right. So okay. So the point that you need to have from here is just that. So this is the reduction in like how much you reduce the potential when you mesh A and B, and actually you will the potential reduction should be kind of as big as this thing. Yeah. Okay. And now I'm gonna say that, okay, if you actually look at this thing, when you sum over all mesh edge, then this is actually big. The total sum here is quite big. Okay. And the reason is this. Well, so, okay. Let's take each term in the sum here. Like I just ignore the n-1 here. Just look at each term in the sum. Okay. So if this is x, b, xa, and xb, so this is like the thing in AI. This is the thing in BI. So I can choose like one point here, eta, which is like the number between AI and BI, right? Okay. And now this thing is just like you look at each match edge and you take the square, but this gonna be at most like at least this thing's square plus this thing square. Okay. And now you can see that this, because M gonna be perfect. Actually, why MI is perfect? Yeah, it's a median cut. So everyone is actually matched, right? And because everyone is matched, then you can, instead of saying that you sum over all match edge, you can write it like you sum over all nodes actually. And now you just write things down, like just expand things. Okay. And this term is gonna be 0. And the reason is, okay. The reason is that x is gonna be orthogonal to 1, right? Because x is just Ri times this thing, but Ri is orthogonal to 1. Yep. All right. Okay. Okay, so like you can verify that like this thing times 1 is gonna be 0 because this is gonna be 1. Yeah. Okay. So that's why this term is cancelled. This term is just 0, and this is positive. So you have that this thing is at least this much. All right. And now, because once you have this term, you can write like we now try to write this term as like we try to relate this term to the potential, basically. And how to do that? So okay, we have that XA is this much, is this thing, and because Ri is just orthogonal to 1, you can safely add this term into your equality. Okay. And now once you have this, then apply this thing again. then you have that, this thing square, like, okay, like this thing is your V, all right? So you have like the norm square here is the norm square as the projection over D, but you have like, but D is n minus 1 and this is just a xa. All right. Okay. Which means that you have that this term is at least this much, but each of this thing in expectation is this thing, or okay. So like this thing over n minus 1. So if you multiply n minus 1 here, this whole thing in expectation is going to be at least this. But this is just your potential. From I minus 1. Okay. So now if I combine everything together, what do we have? We have that, let's look at the expectation, like how much your potential decrease in expectation. What is expectation over? Just over the random direction. So what do we have? We have that, okay, by 6. By here, like the potential reduction is decreased by exactly the distance square for each node, for each match edge. So you get this, but this term here is gonna be like at least, like this is the distance square before projection, but after you project, the distance square is gonna be something like, it's kind of preserved. This is the distance square after projection, but like you should think of it as like these things are preserved. You might lose a log factor, but that, like you cannot lose more than log factor with high probability, right? And I have this this term here just because of the dimension thing. Yeah. Okay, but this whole thing, we just saw that this whole thing is gonna be big, which is something like this. So basically, in expectation, you decrease your potential by log n factor, like by 1 over log n factor of your potential before. Which means that, like, in expectation, the potential at I is like, you reduce it by like 1 minus 1 over log from previous potential. So if you do, once you have this, then it means that this process, you cannot like proceed by more than log square round, because if you proceed by more than that, like after log square round, you, like with high probability, you're gonna be small, right? It's like this thing to the log square is now like poly n. Okay. Yeah, this is just a bit. Yeah, the proof is just like maybe I'm not very good with the algebraic proof too, but yeah, like, but the explanation that I want you to have in mind is just this part. This part where the fact is that you just really think of each point as like it's like it lives in a dimensional space, and because you project things down in the random direction and choose the median cut, then you really like the matching should really like correspond to the 2 point that like okay. If you project it down to here and choose a median cut, the 2 point here which have large distance after projection should have large distance before in original space too, and that's why the potential reduction should be big. Yeah. So that is why everything really works. And you can see that, okay, so that's done. Like once potential is small, then you have that, like once potential is like small, then you have that every node can send flow to every node with at least 1/n something. And once that happens, we have that the graph is indeed an expander, right? Where is it? Here. Once the potential is small, then every node you can send flow to V by some amount like 1/n, and this means that the graph is a expander, have high expansion. Okay, so that complete the correctness, and again for running time we see that like you can compute x in each round in just a times I time by multiplying like one vector by one, like multiplying this and then here and so on. So in total, and because the total like there are like log square rounds, so the total time is something like for each round you spend this much time. Oh, okay, is ni for multiplying x and n log n for sorting, just for sorting. And so the total time here is gonna be something like n I last square, right? Which is n to the n times log to the fourth. Oh yeah, that's true. So actually we don't need this term. Yeah. Yeah, but this still dominate things. Yeah. Yeah. Right. So yeah, so you can see that actually this is kind of it should be implementable actually, right? You really like have some matching and you multiply thing, just multiply vector to some sparse matrix and sort. So this is quite simple. Okay, so that complete the proof. Now I want to tell you about the state of the art a bit. So there are other randomized algorithm actually that is slower, like maybe it's like n times log to the 12 or 8, I'm not sure. But it's a bit better. So that is, it says that at the end the expansion is at least log n after log square rounds. Like what we showed today is just expansion is at least like O of 1. But note that expansion can be more than 1, right? Because it's not conductance. Conductance is at most 1. Expansion can be more than 1. Can be as big as the max degree. Yeah. So they show that expansion at the end of different algorithm can be O of log n, omega log n. So a bit better. Yeah. Like just for the same number of round, like similar number of round, you get better expander. Yeah. So you have this much, which means that the conductance is this much. Right. Okay. So, okay. And we kind of saw slow deterministic algorithm and fast randomized algorithm. But there are like algorithms that kind of give the best of both worlds. It kind of show that in each round you spend like almost linear time, not n polylog, but n to the 1 plus little 1. So that after log n rounds, your graph is like 1 over n to the little 1 expander. Not 1 over polylog, but still not too bad. And yeah, the big open question that I really wanna know like how to solve is, can you shave this thing out? Like, can you make it polylog and make this polylog too? Once this is solved, like you will see later, maybe next class, that like cut matching game is really like the core subroutine that enable a lot of things based on expander to be fast. And because of this, it allows all of the things that based on expander to be deterministic and fast, but not quite, because there is this n to the little 1 thing. If you can remove all of this little 1 here and make it polylog, then a lot of deterministic algorithm based on expander gonna be sped up. Yeah. Okay. And okay, one small project that I think may be interesting to look at is, so in randomized algorithm, I said that we're gonna choose R to be a random vector, right? R is unit vector such that R is incident, like orthogonal to 1. And here we, like, in the analysis, we really think of R as like something that is random in the n-dimensional space. Like, it's not really like, maybe like it's from real. Like, so it's not clear how to implement that like efficiently, or how much precision do we need to really implement this R, to really sample this random vector R. What if we just instead say, like, similar to our power method, say that choose R to be a random node, random point in the hypercube, choose -1 or 1 randomly, and just make it, then just translate it to be orthogonal to 1. I think this should work too, but I like, we need to make it, like, analyze it. But this should work, I think. But if it works, it's gonna be like much better to implement. Okay. And just want to mention further topics regarding cut matching game. So here we really talk about how to implement, how to construct undirected expander in this kind of framework, right? We can talk about directed graph too. So here the game is very similar. You have rounds, and in each round, let's say that the card player choose, instead of a card, maybe it choose two set. I say it's similar to a card, but let's say I choose two set of with the same size. And then what matching player need to do is that it need to add matching on one side and maybe different matching on other side. Yeah. And then your graph is just a union of matching on both sides in this round. And keep doing this for many rounds. Then like the algorithm that we saw in class, both algorithms actually can generalize to the directed case actually. So by which I mean this, that there are algorithms for card player such that after log n or log n square rounds, then what you have is that the graph after the last round is an expander in the indirected sense. That is, if you look at any cut S, then the number of edges going out of S is big compared to S, but also the number of edges coming into S is big compared to S too. Like both of these is big compared to S. So this is called maybe directed expansion. And you're gonna have that this is at least one after log n rounds or log square round. So you can have a look if you want to look at it. It's kind of more difficult to prove, like more technicality, but it works. And like this is why I kind of like in the first half of the class I kind of said that okay, we have seen a lot of equivalence about expander, but that is about undirected expander with edge expansion, right? So that theory is for the undirected graph, but here actually cut matching game works for building directed expander too. And this is why like cut matching game is kind of flexible enough to give you some algorithm for directed graph too, actually. Okay. And there are lower bounds. Like you might ask, like, can you reduce the number of rounds from log n to log, say? But it turns out that people say that okay, if you want expansion to be constant, then you need square root n number of rounds, or if you want something else, then the number of rounds need to be like log n. So I don't completely understand this low bound actually. For example, what if we just want to say that we just want the expansion at the end to be 1 over polylog? Can you actually get can you make the number of rounds to be small? Is it true that this lower bound just extends seamlessly to this case too, when you just want 1 over polylog? I'm not sure. Yeah. But you will see that if you can reduce the number of rounds, that's gonna be good. We will see this later. Yeah. Okay. So there are some exercise, but I talked about this maybe on Friday. Oh, tomorrow. Yeah. So And okay, next week, we're gonna see how to use cut matching game to